This is Marco Miranova reviewing Taylor-Adkins problems. Question 1. Question 1, Part A, applies specifically to the Bernoulli equation. From the problem statement and the given data, we first record down the Bernoulli equation and write down our assumptions. The Bernoulli equation that we write down must be the extended form, including work and/or friction. We are also able to assume, however, that there is no work on the system being done, that there's a horizontal flow in this system, the density of water, and that the system is at steady state. Crossing out the two heights as everything is in the x direction, we apply the continuity equation to find the velocity of the fluid. From there, we plug in all of the given variables after rearranging for the pressure, of course, and solve for the difference in pressure of the system. It is noted that friction here is defined as the head loss times gravity. The reason it's defined as such is because it allows for the units in the equation to be consistent, as the Bernoulli equation can be written in head form or in regular form. And this particular equation is written in normal form. Part B of question 1 takes the previous problem statement and expands it by having us apply a macroscopic momentum balance on a cart that is being pushed by the fluid acting upon it. We are able to create new assumptions, including that the velocity or the relative velocity of the fluid is equal to the velocity of the jet right here minus the velocity of the cart that is perceived and calculated to be. We are also able to make the assumption that the weight of the cart is negligible, which is applicable in our momentum balance. We start off by calculating the relative velocity by plugging and chugging using given variables. We proceed to writing down the momentum balance with the frictional correction factor, even though it is stated to be 1. Applying the momentum balance with crossing out the assumptions that dm dt and dv dt, as they pertain to time, are able to be canceled out as the system is steady state, we result in the following equation. Forces in the x direction pertains to the force of the brake. As the force of the brake is equal to here, to this equation right here, but in the opposite direction, this is our final equation. Plugging and chugging, we get an answer of 55.37 newtons. Question 2 addresses hydrostatics and buoyancy, topics 1 and topic 2. Topic 1 is assessed in part B. Hydrostatics involves calculating the different densities and the weights and the pressures that those particular fluids correspond with. Given the picture and given these defined variables, we are able to set up a balance of pressures. Going through the pressures, plugging and chugging them in, we get 59.19 kilopascals. Part A assesses topic 2, buoyancy. It is asking for the buoyance force on the man in the pool. The buoyancy equation is as follows. Density is mass divided by volume, so we are able to solve for the volume of the man. Plugging and chugging things in, we get that the buoyant force acting upon the man is 363.95 newtons.